Thanks for the introduction, and thanks Ines and Till for organizing this exciting symposium. It's a great pleasure to be here. I really hope you all had a good night of sleep, but I think it's more accurate to assume that many of us did not get sufficient sleep in the course of this conference. And the bad news is if you actually have insufficient poor sleep over longer time periods, this has bad consequences on our brain and body functions. And of course, over longer time periods, this can also be detrimental for our health. But what part of sleep is actually important for health? And can we further boost it to even make sleep more efficient and sleep healthier? And related to that question, it's very important to take into account that sleep is not just a single process, right? It's made up by different brain activity patterns, so-called sleep oscillations. Well, I'm always still very fascinated when I look at EEG from a person in wakefulness and then I look into non-rapid eye movement sleep. And there's this dramatic change in brain activity. And during non-REM sleep, you have two dominant sleep oscillations, the slow waves and the sleep spindles. And the slow waves are these high amplitude, low frequency waves that can be generated by the neocortex. And they reflect how deep we are asleep. So the more we have of those, the stronger they are, the deeper we are asleep. And then we have the sleep spindles, which are more transient events. They occur for a few hundred milliseconds and then they vanish again. They are around 11 to 16 hertz and generated by the thalamocortical system. And these oscillations are likely the carriers for the restorative effect sleep have, but still we have a very limited knowledge about what their function actually is for us. So today I will take you on a journey like showing the research development path of these sleep oscillations. It's actually reflecting my path, but I also think it's where the sleep research field is heading to. And so first I will show you some studies illustrating that there are many correlations of these sleep oscillations to brain and body functions. But then I want to move to causality and see what their real function is by using non-invasive brain stimulation. And then I want to highlight how important it is to also go application-oriented, which is my current project, actually to go into long-term studies and see whether really changing those oscillations over longer time periods can really be transformative to promote health. Well, and I think an important move into this direction is also to go actually from in-lab studies to in-field studies to do that. Well, there have been many studies showing that sleep oscillations are correlated to brain functions. For instance, we and others have shown that sleep spindles are predictive for memory consolidation. And the same holds true for slow waves. Also there, correlations with memory consolidation have been found, but there's also a relationship, for instance, to cortical development and development of motor skills. But the correlations actually have not been restricted to brain functions. In fact, there are also many studies showing that brain oscillations during sleep are predictive for peripheral body functions. And one example is that slow waves are related to the nocturnal release of hormones that are involved in muscle and bone metabolism. And slow waves are also related to the regulation of the heart. But correlation does not imply causality, right? So do we just see now an epiphenomenon here, or is there really a causal role of these oscillations? And for that, we have to go into brain stimulation. And in humans, of course, it's very attractive to go into non-invasive approaches to do so. And we have heard here in this conference about many different possibilities. For sleep oscillations in the last decades, I think there are two, at the moment, very promising tools to do these manipulations. And one is transcranial current stimulation, and the other one is auditory stimulation. And today I will go a little bit more into detail, both of them. Well, I think most of you know what transcranial alternating current stimulation is, but I still give a quick reminder, and I also want to go a little bit more in the possible mechanism of how it could work. Well, when we apply TACS, we apply a very weak current to the scalps where electrodes are attached, and these currents are at the very specific frequency we are interested to stimulate. And I think it's again very important to point out that these fields are very weak. So it's a subthreshold method, which means we don't directly induce new action potentials, such as with TMS, but we rather modulate and shape ongoing endogenous oscillations. And the question is, how could something like that work, right? If we don't change directly induced firing, how could we actually change brain activity? And to understand that, I think we have to go a little bit more into how neurons communicate. Most of you probably think about chemical and electrical synapses, but there is a third way how neurons are actually communicating, and it's so-called ephaptic coupling. So if many neurons are active together and synchronized, they generate endogenous electric fields that actually can be picked up with our current methods, the EEG and the LFP. And for a long time, it has been thought that these oscillations are mainly reflecting brain activity, but actually they take an important and active role in shaping network activity. Specifically, actually, the spike timing and also large-scale synchronization of networks. And these endogenous electric fields are actually very weak. They're only 1 volt per meter. And to put that number in perspective for you, you need around 20 volts per meter to induce an action potential. But it also means that if we actually apply an exogenous field, we might be able to also shape network activity. But related to that, it's also very important to take that into account when you do a rational design of stimulation. Because we cannot just apply anything we want, any frequency we want with TACS and hope it's actually improving. I think we have to take into account that according to the dynamic system theory, the brain has oscillators, right? And there is already an intrinsic ongoing frequency, and you can actually enhance frequencies that the oscillator is preferred to actually oscillate at. And according to the Arnold's tongue, this principle, it's basically the idea that if we enhance or if we apply frequencies that are very close to the intrinsic frequency, we don't need very high stimulation amplitudes, but if we go further away, we have to have stronger fields, and at one point they have to be supra-threshold to actually override existing stimulation, existing frequencies. But I think it's very important that we have to know that the network has to be very close to threshold that we are already able to change something with TACS. Now, we took this principle into account when stimulating sleep spindles, because one challenge with sleep spindles is they are not occurring like continuously. During non-REM sleep, they are transient events, so they're only occurring for a few 100 milliseconds and then they vanish again. So we developed a feedback-controlled system that was able in real time to detect whether the person is in non-REM sleep, and then also in real time detect whether there is a sleep spindle. And we only applied electrical current in the spindle frequency range when a sleep spindle was actually there. Now, with this method, we increased spindle activity in a very specific window after stimulation. And as I told you before, the main interest is, of course, to see what is the behavioral consequence of doing such a stimulation. So at this time, I was really interested in memory consolidation. We know sleep is actually benefiting memory, stabilizing memories or enhancing them. And one very famous task to do is this motor sequence tapping task. We see people get faster when doing it. And of course, after a night, there is even like a further jump in this performance. After applying the stimulation, we saw that this speed enhancement component was actually further increased. And we also saw that the enhancement of sleep spindle we saw with this stimulation was predictive of how much the participants improved in this motor sequence tapping task. So we actually had first evidence that sleep spindles seem to be functionally important for motor memory consolidation. But there's also a very clear drawback to this method, right? I think a lot of you saw, I just show you a picture of what happened after the stimulation, because we still are really challenged with the fact that we cannot remove the artifact from the EEG. And there, of course, have been a lot of critical voices in a sense like what really happens during stimulation, and that still needs to be established also in animal studies. And with that drawback, I actually come to another stimulation modality that does not have this issue, namely auditory stimulation, because there we actually directly go supra-threshold, we induce spiking, and we also have no artifact in the EEG. But what happens in the brain when we play different rhythmic stimuli? And what I can tell you already now is it's depending on the vigilant state we are in. So it's not the same during wakefulness and during sleep. And this has been shown already years ago, and we recently looked at that on a topographical level. So we had high-density EEG in 14 subjects, and they came for one afternoon into our lab. And they had 2 wakefulness sessions interleaved with a nap session. And during these sessions, we had a very specific type of sound we played. They had continuous white noise, and it was amplitude modulated at either 40 hertz or 14 hertz. And you want to see what the response to these stimuli is. So now I just show you the response to the 40 hertz. What you can see are the classical responses you actually expect in both vigilant states, wakefulness and non-REM sleep. You see an entrainment to the 40 hertz, which is basically the frequency you apply to, and then you have the classical ERP components to the tone onset, and to the tone offsets, that is in the theta and delta range. But it also already shows that at least on average here, the magnitude of this response seems to be different between vigilant states. And for the 40 Hertz entrainment, actually, I show you here like the topographical distribution of it, so for wakefulness and non-REM sleep, and we see that for all 3 conditions I compare it to, the topography looks actually similar, where the maximum is, but for non-REM sleep we see a very clear reduction in occipital regions. And it's interesting because I think a lot of people have used these auditory sounds to track different states, also for instance the death of anesthesia. But I was actually even more interested in to see what are the non-classical responses to these auditory stimuli. Can we use them to induce sleep oscillations? And yes, we can. So when we look at the 14 Hertz stimuli, we realized that when they were played during non-REM sleep, there was an increase in spindle activity. And we also saw it's not just an increase in spindle activity. Actually, when we looked at and we do an automatic detection of sleep spindles, we realized that the probability of having a spindle in the window when this 14 Hertz stimuli was played was significantly higher compared to sham, where we basically only had white noise. And again, I think important is also to say, well, maybe we just induce power in this frequency range because we apply this frequency. But interestingly, when we look into a wake condition, there is no increase in this spindle activity. So it's very vigilant state specific. And here we just see that on a topographical level as well, and with statistics. So during wakefulness, there is almost no increase in the spindle activity, but during non-REM sleep, you have a strong one. It's, of course, significantly different between the conditions. Now, I think this method is also interesting to go into and look into behavior. That's actually one of the next steps we are doing. But sounds have not only been used to change sleep spindles. In fact, there are clearly more publications in using very special sounds to change slow waves. And the idea there is actually you have to be very precise in timing when you apply these stimulations. So if you play a sound, and it's around 50 millisecond pink noise, as an example, when the slow waves are going up, so in the up phase or in the up state, then you can further enhance the amplitude of the subsequent slow waves. But if you actually do it at another time, namely when it's going down or the down phase, others have shown that you can also suppress slow waves. And it means actually we have to be very careful when we time those sounds that we are actually not suppressing slow waves if we want to enhance sleep. And it again needs actually feedback controlled systems to do so. One problem at the moment with this method is even though it's like very promising, there are only a few studies. So first of all, we don't really know what the mechanism is behind it. And we also don't know what the optimal settings are. Likely for individual population, individual different people, the settings, how we apply the stimuli might be different. And another important point is we don't really know what the long-term consequences are. I mean, all these studies that have been done with brain stimulation are single session studies, single night studies showing effect on slow waves and also sometimes an effect on behavior such as memory consolidation. But we actually have no idea whether over longer time periods we really make a difference, right? Whether we really can promote health. Actually, to be able to do that, we need to go from the sleep lab into the field. And just a quick recapitulation, what actually happens in a sleep lab when we do such an experiment, we have a participant and a biosignal amplifier. We record different signals such as EEG, EMG, and EOG, and then there is a very good computer doing real-time processing of the signal, timing the sounds. But we also need an experimenter that controls the stimulation, make sure that the person is in sleep, and then starts the algorithm to run and make sure everything is correctly done. And actually in the last year, we moved the whole sleep lab into a little box, actually, so that I can hold in my hand and participants can use by themselves. And with that, we can actually see what the long-term consequences are of these enhancements. Here I just show you one pilot participant and one example where we had the algorithm run and stimulating the up phase of slow waves with tones, but we had like 6 seconds of stimulation and then we had an off window just to compare how the slow waves differ between the two windows. And what we saw is that there is a highly significant increase in the slow wave activity when the sounds were played compared to stimulation windows where this was not happening. Now I think I actually want to finish my talk with showing where we are and actually where we have to go. So I think there have been many approaches stimulating slow waves and sleep spindles, and already many studies actually have established that sleep seems to be important for certain brain functions, such as memory consolidation, but there is still a long way to go. What is interesting though, there are many studies showing that there are relations to body functions apart from the brain. And interestingly, we have almost no knowledge about what actually the consequences are of changing brain activity and what happens actually in the body when we do that. So with the stimulation modalities we have at the moment, we can actually combine it with peripheral measures and see what the consequence is. And then we also again have no idea what the long-term consequences are. Can we really change brain and body functions and really promote health? And for that we actually can use now these portable solutions. And I think it's a very serious point because there are many conditions that involve reductions of these sleep oscillations, and I think there's one that affects all of us, which is aging. We see a dramatic decrease after puberty until we get older in these low waves, and maybe they are also part of actually the disease process, so this reduction, and hopefully with the methods we establish, we can also promote health and reduce the burden of brain and body disorders. So I would like to thank actually the teams involved. So currently I'm in the mobile health system lab at ETH, so I thank the people involved in also developing these devices and all the collaborators we have, and the University of North Carolina, and the people there, because the work I showed in the beginning with the feedback controlled spindle stimulation and auditory stimulation was done in this lab. And if you're excited about outcomes of the first clinical trial we do with now this device, go to sleeploop.ch, so we will actually update on findings we have related to that project.